Imagine this. You are standing in an empty field on a silent night. No wind, no noise, just darkness stretching in every direction. You lift your head and stare upward. Above you, stars burn like scattered sparks across an ocean of black. From the ground, it looks peaceful, still, almost simple. But this calm sky is a lie. Space is not quiet. Space is not empty. Everything your eyes can see and everything that your instruments can measure exists within something far stranger than a void. It exists within a structure built from invisible directions that guide every motion, every orbit, every breath you have ever taken. We live our lives inside three familiar dimensions: length, width, height. They are so ordinary that we never question them. You can walk forward or backward. You can step to the side. You can jump upward. Every action you take is just movement across these three directions of space. An entire lifetime passes, and most of us never imagine anything beyond them. Then there is time. Unlike the other dimensions, you cannot freely choose your direction along time. You cannot stand still in the present and then walk backward into yesterday. Time pushes us forward, moment by moment, and we have no option but to follow. Together, these four directions form something called space-time. It sounds abstract, but space-time is the most practical idea in physics. It describes where you are and when you are. It is the stage on which every event in the universe unfolds. More than 100 years ago, a young patent clerk named Albert Einstein revealed that space and time are not separate. They are woven together. When mass appears in space-time, that fabric bends. The bending is what we call gravity. We do not feel gravity as a pull. We are falling along the curves of space-time itself. When a planet loops around its star, or when the moon circles the Earth, nothing is pulling anything. The bodies are simply traveling along the shape of space-time. Every orbit is geometry in motion. Once you see gravity this way, the world becomes almost elegant. A marble rolling inside a curved bowl does not need to understand the shape beneath it. It just follows the surface. The Earth does the same thing around the Sun, and the Sun itself does the same around the center of the Milky Way. Everything, from galaxies to wandering asteroids, moves because space-time tells it how to move. So, if the universe follows this perfectly balanced geometry, why does something feel incomplete? Why does physics still contain cracks and puzzles that no one has solved? The first clue is hiding in plain sight. Gravity is unimaginably weak. If you hold a simple refrigerator magnet and use it to lift a paperclip, that tiny magnet wins against the entire gravitational pull of planet Earth. In other words, the electromagnetic force from a small object in your hand overwhelms the gravity of a world with more than 500 trillion kilograms of mass. Something about that makes no sense. Why should gravity, the force that sculpts galaxies and shapes the entire universe, lose to a cheap refrigerator magnet? Electromagnetism is stronger than gravity by roughly 10 to the power of 36. To make that number real, imagine that gravity is as thin as a single human hair. In that comparison, electromagnetism becomes a mountain the size of Everest towering above it. These forces are supposed to be part of the same universe. They should follow the same rules. Yet one governs everything, and the other barely holds dust together. Physicists call this puzzle the problem of weak gravity, and it continues to haunt modern science. Every other force of nature fits into our mathematical understanding. The strong nuclear force binds the heart of atoms together. The weak nuclear force is responsible for radioactive decay. Electromagnetism holds matter together and shapes chemistry. All three can be described by quantum theory, a framework that predicts their behavior with astonishing precision. But gravity refuses to fit into that same framework. Gravity lives in the smooth curves of Einstein's space-time. Quantum theory lives in the jittering, chaotic world of particles and probabilities. When scientists try to combine them into one picture, the mathematics collapses. It is like trying to write a novel using two different alphabets that will not mix. One works for large objects like planets. The other works for tiny objects like electrons. Neither can speak the language of both worlds. Yet the universe clearly operates as a single system. The contradiction forces a disturbing possibility. The universe feels strange because we might be seeing only a fraction of its true structure. If gravity is weak because we are only feeling a small part of it, then the rest must be going somewhere. It must be flowing into something we cannot see. Imagine shouting into a room and hearing your voice soften. Not because you are quiet, but because the room opens into a hallway you cannot step into. Your sound spreads farther than your senses allow. The same might be true for gravity. What if gravity spreads into a hidden direction, a direction that exists alongside length, width, height, and time? Not metaphorical, not symbolic. A literal, physical direction that we cannot move through. If such a dimension exists, the majority of gravity could be leaking into it. We would only feel the leftover remainder. The weakness of gravity would not be a flaw in nature, it would be evidence of an unseen dimension. This is where the story shifts. For thousands of years, humanity believed Earth was the center of everything. Then we learned the Earth orbited the Sun. Then we discovered the Sun was just one star among hundreds of billions inside the Milky Way. Then we learned that galaxies themselves are scattered through the universe in numbers too large to count. Each discovery was not just a new fact, it was a blow to human certainty. We never stood at the center, we only stood in our own small corner. Now physics is whispering something even more unsettling. We may not even be living in the center of dimensions. We navigate only 3 directions because those are the only directions we can perceive. But perception is not truth. A 2-dimensional creature living on the surface of a sheet of paper would never imagine the direction of up. A 3-dimensional creature, like a human, might never imagine a direction beyond the space we can move through. The universe may feel like the whole of reality, when in fact, it is a boundary of something larger. If gravity flows into a hidden direction, then our universe is not the container. It is the surface of a greater shape. The idea sounds bold, it should. But soon, a single physicist will dare to test this idea in a way no one had ever attempted. He will add one more dimension to the equations of Einstein, and by doing so, he will accidentally discover something astonishing. He will unify gravity and electromagnetism without even trying. The idea of hidden dimensions does not begin with modern physics. It begins with a question older than telescopes. Why does the universe behave the way it does? Why does gravity guide planets with such precision? Why do galaxies form spirals so enormous that whole civilizations could rise and collapse before a single star completes an orbit around the center? The night sky gives us patterns that appear permanent. The universe looks balanced, predictable. But the deeper we search, the more the structure of reality behaves like a puzzle with missing pieces. Scientists measure the movement of stars around galaxies and discover that the stars are traveling far too fast. They should fly outward into empty space, yet they stay bound together. It is as if something unseen is holding them, something with mass, something that does not emit light. They name it dark matter. The name does not explain it. It only represents our ignorance. Then they measure the expansion of the universe and find that instead of slowing down, the expansion is speeding up. They call this dark energy. Again, the name solves nothing. It is just a label placed on our confusion. When you list the contents of the universe, something shocking appears. Everything we can see, every star, every planet, every cloud of gas, every atom on Earth, all of that adds up to only a tiny fraction of the universe. Less than 1/20th of the total. The overwhelming majority is invisible. We know it is there only because space-time bends around it. The invisible sculpts the visible. This is where the cracks in our understanding begin to spread. We treat space-time like a stage. But what if space-time is not a stage at all? What if it is a surface, a boundary, the thin layer of something that stretches deeper into reality than we can ever travel? If that is true, then gravity might not be weak. It might simply be diluted across hidden directions. Imagine a child stretching a sheet of rubber across a frame. A marble placed on that sheet sinks slightly, creating a gentle curve. Now imagine that the sheet is just the surface of a sphere, a ball. The marble still sinks, but most of the curvature spreads into directions you cannot see from the outside. You are only seeing the imprint on the surface. This is the possibility physics now considers. Gravity may be spreading across more directions than our senses allow us to perceive. Selective blindness is not a new phenomenon in nature. A bee sees patterns in flowers that humans cannot. A snake senses infrared heat from the bodies of other animals. A bird detects magnetic fields as if they were colors painted in the air. These creatures are not seeing illusions. We are the ones who are blind. Reality does not limit itself to human perception. Humans limit reality by filtering what they can understand. So when physics tells us that extra dimensions could exist, the idea is not reckless, it is humble. The first mathematically rigorous attempt to describe an extra dimension arrived in the early 20th century. Before the era of rockets, before the discovery of nuclear forces, before quantum theory took shape, the world was recovering from the shock of Einstein revealing that space and time are fused. Mathematicians were trying to catch their breath from that revelation. And into that moment stepped a bold thinker named Theodore Kaluza. He did not search for an extra dimension because it was fashionable. He searched because he saw something elegant in the structure of Einstein's equations. The existing 4 dimensions did not leave room for electromagnetism to be fully unified with gravity. But if he added one more direction, even if that direction was tiny and unreachable, the mathematics changed. It bloomed into something new. Gravity and electromagnetism fell out of the same geometric structure. No separate theories, no additional assumptions, just a universe with one more direction than anyone imagined. When he sent his work to Einstein, even Einstein hesitated. The idea felt outrageous. The mathematics felt too smooth, too perfect, and perfection in science is suspicious. Yet after examining the results, Einstein approved the publication. The world now had a theory in which electromagnetism emerges from geometry that requires a 5th dimension. But if that extra direction exists, why do we not see it? The answer lies in scale. Consider an ant walking along the surface of a garden hose. From far away, the hose looks like a simple straight line, a single dimension. But the ant experiences something different. It can walk forward and back along the hose, yet it can also walk around its surface. The hose reveals a hidden direction that a distant observer cannot perceive. The extra dimension is real. It is simply too small to detect without looking closely. Oscar Klein later proposed that the 5th dimension in Kaluza's theory is curled into a tiny loop. So tiny that even the most powerful instruments today cannot observe it directly. This idea introduced the concept of compactification. Dimensions can exist without being large or noticeable. They can be folded tightly, hidden inside the structure of reality itself. Here is where the story becomes cinematic. In modern physics, the size of this curvature is so unimaginably small that to probe it would require an energy level near the Planck scale. That means a scale at which space and time themselves begin to vibrate with quantum uncertainty. To reach that energy would require an accelerator the size of a galaxy. Humanity does not have that capability. We do not even have the knowledge to build such a machine, but we can look for indirect signs. If gravity truly spreads into a hidden direction, it should occasionally behave as if some of it vanishes into thin air. During high-energy collisions, particles might appear to lose momentum without explanation. The missing energy would not disappear. It would flow into a direction we cannot see. We have already built machines that can search for this. The Large Hadron Collider in Switzerland smashes particles together at nearly the speed of light. Millions of collisions occur every second. Scientists search each collision for one specific signature, something that proves gravity is slipping away, missing energy. If we detect it with the correct pattern, if we rule out every known interaction, if we see energy lost only in the gravitational sector, we will have the first physical evidence that dimensions beyond 4 actually exist. And perhaps most astonishing of all, we might find that dark matter is not some exotic, invisible substance. It might be ordinary matter located in another dimension. Matter that interacts with gravity across dimensions, but not with light inside ours. If that is true, then the darkness of the universe is not empty. It is full of worlds we cannot reach, and gravity is the only whisper between us. The universe is not just stranger than we imagine. It may be stranger than we are able to imagine. The idea that we might be living in only a fraction of reality forces a deeper question. What exactly is a dimension? We use the word casually, but the meaning is precise. A dimension is a direction in which something can move, or a direction in which something can change. You can slide a cup across a table because it can move forward or backward. That is one direction. You can slide it left or right. That is a second direction. You can lift it upward or set it down. That is a third. If something can vary along a direction, that direction exists, whether we notice it or not. Time behaves the same way. Every moment that ever existed, and every moment that ever will exist, lies somewhere along the timeline. You cannot reverse your motion along time, but you are still moving through it, carried by the physics of the universe. In that sense, time is as real as length or height. You do not need to touch it to prove it is there. You only need to grow older. So if an extra spatial dimension exists, we should expect it to be real in the same way time is real. Not a fantasy, not a symbol, a direction, a place where nature can store information that we cannot see. The thought seems unsettling only because our senses evolved to navigate the world at the scale of trees and rivers and mountains. Our ancestors survived by noticing animals in the grass, not by detecting hidden geometry in space-time. Human perception is not a measure of truth. The silence of space has a way of inviting grand illusions. When astronauts in orbit look down at Earth, they see a world defined by delicate curvature. They see that borders are imaginary. They see that space is not empty. Even light passing from a distant galaxy does not travel in a straight line. It bends as it moves through curved space-time. We call this gravitational lensing. When scientists observe a quasar in the deep universe, they sometimes see multiple images of the same object because the path of its light has been redirected by invisible mass. The universe is like a hall of mirrors, shaping light with gravity. Yet we continue to talk about empty space, as if emptiness could control the path of a photon. The truth is that space tells matter where to go, and matter tells space how to bend. With every step we take, we are walking across a four-dimensional tapestry of geometry. We do not notice it because the fabric is smooth, but sometimes the illusion breaks. When a star collapses under its own weight and forms a black hole, space-time folds so sharply that nothing can escape, not even light. The event horizon marks the point where the curvature becomes infinite. Time and space trade roles. Space flows inward like a waterfall. Time becomes a direction, leading inevitably toward the singularity. At the center of a black hole lies a point where our physics breaks down, not because the universe fails, but because our equations, built from only 4 dimensions, are incomplete. To understand that center, we need quantum gravity. And to build quantum gravity, we might need more dimensions. Perhaps one more, perhaps many. Modern theories like string theory suggest that the universe may contain 10 or even 11 dimensions. If that is true, then our 4-dimensional reality is only a small part of a much grander structure. Imagine a violin string. When it vibrates, it creates sound. But if the string were allowed to vibrate not just forward and backward, but also in hidden microscopic directions, the pattern of the notes would change. According to string theory, the particles that make up matter are like tiny vibrating strings. The frequency and pattern of their vibration determine their properties. The hidden dimensions determine the notes. The structure of reality may not be built from particles, but from vibrations shaped by extra dimensions. There is a moment every scientist experiences when they realize that the universe is not required to be understandable. Reality will not simplify itself to suit our comfort. If there are more dimensions, they will exist whether humanity accepts them or not. Our task is not to approve the truth. Our task is to discover it. Perhaps that is what makes the pursuit noble. We are creatures of 3 space directions and 1 time direction trying to imagine a geometry that extends beyond all that we know. We are like fish in a pond attempting to conceive of flight. The pond is everything we have ever seen. The pond has rules. Light bends in certain ways. Matter moves in certain ways. The surface of the pond ripples, but the fish cannot imagine the wind that creates the ripples. What if we are in our own cosmic pond? What if space-time itself is the shallow surface of a deeper ocean of dimensions? We ride the surface tension between what we know and what we cannot see. Gravity might be the one clue that refuses to stay on the surface, a whisper leaking from below. As we turn toward the next chapter, we return to the moment when one human mind saw beyond the familiar. Theodore Kaluza dared to write a 5th direction into the mathematics of our universe. He did not know that future generations would build particle colliders, observe gravitational waves, or scan the sky for dark matter. He only knew that the equations led somewhere new, somewhere beautiful, somewhere terrifying. He followed them, and when he did, he became the first person in history to reveal that an unseen dimension could unify the forces of nature. The story begins with an idea so unusual that even Einstein hesitated to believe it. A new dimension, a direction beyond the 3 we move through and beyond the single direction of time that carries us forward. A hidden corridor of reality that we cannot touch or see, yet one that shapes the universe from beneath the surface. The person who first dared to write this extra direction into the mathematics of nature was not a celebrity in science. He was not a physicist who filled lecture halls or dazzled crowds. His name was Theodore Kaluza, a quiet thinker working alone in a modest office. Kaluza looked at Einstein's equation, the one that describes how matter bends space-time and how space-time tells matter how to move. Instead of admiring its perfection, he wondered if something was missing. He wondered whether the strange division between gravity and electromagnetism was a sign that our picture of the universe was incomplete. Gravity was geometry. Electromagnetism was something else entirely. Light behaved as a wave, but also as a particle. Electric fields and magnetic fields intertwined in beautiful patterns described by James Clerk Maxwell, yet no one knew why they existed at all. They simply were. Kaluza wanted more than a description. He wanted a reason. With a quiet audacity, he imagined one more dimension tucked into the fabric of reality. He did not try to visualize it. He did not give it a mystical purpose. He simply wrote the mathematics as if reality contained a 5th direction. What happened next did not feel like invention. It felt like revelation. When Kaluza allowed space-time to stretch into that hidden direction, the equations changed. They unfolded. They revealed something astonishing. Maxwell's equations, the laws of electromagnetism, emerged naturally from Einstein's theory of gravity. No extra assumptions, no elaborate machinery, just pure geometry. The universe suddenly looked like a single structure, not 2 separate ones. When Kaluza sent his manuscript to Einstein, even Einstein needed time to absorb it. The idea appeared almost too elegant. The equations of gravity and the equations of electromagnetism, both emerging from the same fabric of space-time, but only if reality possessed a 5th dimension. Einstein finally replied that the idea was interesting, and then he allowed Kaluza's work to be published. But the world barely noticed. The idea seemed more like fantasy than physics. No one could see a 5th direction, so few were willing to believe it existed. Years passed. Kaluza's work remained a curiosity. Then another mind stepped into the mystery. Oscar Klein, a Swedish theorist, asked a simple question: if there is a fifth dimension, why do we not see it? His answer was profound. Maybe the fifth dimension is real, but it is curled into a loop so small that we cannot detect it. Klein imagined this extra direction as a tiny circular pathway folded into every point in space. If you could shrink yourself to a size smaller than a proton, perhaps smaller than the Planck length itself, you might walk along that hidden direction. But at the scale of humans, planets, or stars, it would be invisible. Think of a drinking straw. From far away, it looks like a simple line, a one-dimensional object, but up close, you see that the straw has thickness. You can move around its surface. A tiny ant walking along the straw would discover a second direction, one that a distant observer cannot see. The straw did not gain a dimension. The observer simply lacked the resolution to detect it. In the same way, Klein suggested that the extra dimension of reality could be wrapped so tightly that only particles or phenomena with enormous energy could move through it. The idea of compact dimensions is not poetic imagination, it is rigorous mathematics. In this picture, the fabric of reality is not flat and featureless. It is textured, folded, and curled at unimaginably small scales. Every particle, every atom, every quantum fluctuation lives in a universe with more directions than we can experience. This idea does not contradict Einstein, it extends him. It suggests that geometry is not only responsible for gravity. Geometry also shapes light, electricity, and magnetism. In Kaluza's time, there were no particle accelerators that could probe the deep structure of space-time. There were no detectors capable of observing subtle hints of hidden dimensions. All Kaluza had was mathematics and curiosity. He trusted the equations more than his senses. The universe does not owe its structure to human intuition. Nature builds itself from rules that exist whether anyone believes them or not. As Kaluza continued to work, he discovered something unsettling. The fifth dimension did not behave like length or width or height. It did not behave like time either. It behaved like something entirely different. The dimension did not stretch outward into space. It curled inward. Every point in space-time became a tiny doorway to this hidden loop. The universe was not expanding into the fifth dimension. It was carrying the fifth dimension inside every location. The truth of the idea was not determined by whether humans could see it. The truth was determined by whether the mathematics worked. Kaluza and Klein showed that if you accept this hidden direction, electromagnetism becomes a geometric effect, not a separate force. The same geometry that bends space-time to create gravity also twists to create electric and magnetic fields. One ingredient, one fabric, one structure. A universe made of geometry and nothing more. Imagine what that means. Imagine that every beam of light, every flicker of electricity, every signal traveling through the air exists because of a direction you will never walk through. A direction that does not stretch beside you but curls beneath reality itself. A hidden loop at every point. A dimension that gives birth to the forces that allow atoms to combine, that allow chemistry to exist, that allow life to take shape. The theory was bold, too bold for the world of the 1920s. It sat in the shadows of scientific thought. Einstein appreciated it, but even he could not fully accept it. Not yet. The world needed a new language to understand dimensions. A century would pass before the idea returned, carried by the rise of quantum theory and later by string theory. While the world changed through war and technological revolution, the fifth dimension waited quietly, patiently, unseen. And yet, the moment Kaluza placed that extra direction into the expression of space-time, something irreversible occurred. Physics learned that our universe could be more than it appears, that the dimensions we see might not be the dimensions that exist. The equations pointed not toward the visible world, but toward a hidden mathematical truth, a truth that demanded we accept a larger universe, Kaluza did not live to see the world understand what he had discovered. His idea arrived too early, like a signal broadcast into a future that had not been invented yet. Scientists of his time admired elegance only when it matched observation, and there was no technology that could even hint at a curled dimension buried inside space-time. The equations worked, yet they felt more like art than physics. Kaluza was a solitary figure. He had no vast laboratory. He had no research group. Just a sheet of paper, a fountain pen, and the quiet courage to write a question that had never been asked. What if reality contains more than 4 directions? Decades passed. The 5th dimension remained a mathematical curiosity, a brilliant idea no one knew how to test. Then, Oscar Klein entered the picture with a realization so strange that even physicists had trouble speaking it aloud. If the 5th dimension exists, it must be tiny beyond comprehension. Not small like a grain of sand or a cell under a microscope, but compact at a scale so minute that even atoms are enormous in comparison. The radius of this curled direction might be on the order of the Planck length, a distance so small that you could divide the width of a proton into a million pieces and you would still be nowhere near reaching it. Klein pictured the 5th dimension as a loop, not a tunnel, not a corridor, not an extra stretch of space stretching outward, a loop on itself, a circle so tight that the very concept of movement through it becomes abstract. Particles traveling through this loop would not move the way we imagine walking along a path. Instead, they would experience the dimension as vibration. A single particle could exist in different vibrational states depending on how it interacts with the loop. Those vibrations would determine its mass and energy, as if the extra direction were tuning the behavior of particles like a musician tuning a string. Compactification, that was the word Klein used. A hidden dimension that is real, but rolled so tightly that you could never travel along it with your body. Only particles with tremendous energy could ever touch that direction. Our senses would be blind to it, just as we are blind to ultraviolet light or to the magnetic field that birds use to navigate. The universe would not change just because humans could not see a part of it. The universe is under no obligation to be obvious. Once this idea entered physics, something remarkable happened. It began to appear again and again. New theories emerged that required more dimensions. Not because scientists wanted bigger universes, but because the mathematics demanded them. Quantum theory tried to connect the forces of nature with geometry, and suddenly the idea of more than 4 dimensions was not a strange exception. It was becoming the natural path forward. Yet Kaluza and Klein remained misunderstood. They tried to unify gravity and electromagnetism without knowing that quantum mechanics was about to explode into existence. They worked before the discovery of the strong nuclear force, before the weak nuclear force was understood, before the standard model of particle physics was built. Their theory stumbled because it unified only 2 forces when physics would later discover 4. It was not wrong, it was incomplete. Still, the idea carried a kind of gravity. When physicists return to their notebooks, when they stare at equations late into the night, they find that extra dimensions keep solving. Problems that 4-dimensional physics cannot. Why is gravity so weak? Why do particles have the masses they do? Why does electromagnetism behave as if its structure obeys a hidden geometry? Every time the questions deepen, extra dimensions whisper an answer. Perhaps the whisper was always there. We simply did not know how to hear it. Near the middle of the 20th century, the world entered a new era. Humans split the atom. Lasers became real. Telescopes scanned farther than ever before. And at the same time, a new theory emerged, one unlike anything that came before. Quantum field theory. The universe became a sea of fields, each field stretching across all of space. Particles became tiny ripples in these fields. The mathematics became too large for imagination, and the need for a deeper unifying principle grew louder. At first, the old idea of the 5th dimension seemed forgotten. Then quietly, it returned. Not in its original simple form, but as the foundation of something far more ambitious. String theory. A theory that began as a way to model the strong nuclear force and grew into the astonishing claim that all particles are not points, but vibrating filaments of energy. A theory that only works if the universe contains more dimensions than the ones we see. It did not require one extra direction. It required many. Physics had circled back to Kaluza and Klein, only now the scale was cosmic. Where Kaluza imagined one hidden loop, string theory imagined entire compact shapes woven into the fabric of reality. Shapes so intricate that the geometry of these tiny spaces determined the properties of everything that exists. If the curled dimensions were shaped one way, electrons would have one mass. If shaped differently, galaxies might never form. Hidden dimensions became not an optional idea, but the blueprint of reality. And again, the same question echoed. If extra dimensions are real, why can we not see them? The answer remains the same. They are too small, too tightly wrapped, too deeply embedded in space-time. To glimpse them, we would need energies beyond anything humanity can produce. We would need a particle accelerator the size of a solar system, or perhaps a way to observe gravity, not through matter, but through the empty geometry of space-time itself. Kaluza did not know any of this. He lived and worked in a world without particle colliders or gravitational wave observatories. Yet his idea did not die. It went dormant, waiting for the century to catch up. A theory can be ignored, but truth has a way of resurfacing. Kaluza's mathematics had planted a seed, and Klein had given it shape. But even with both contributions, the world of physics was still not ready to accept a universe built from hidden directions. Science does not move by elegance alone. It moves by evidence. Theories must make predictions that can be tested, not simply admired for beauty. For decades, the fifth dimension lived only on paper. The equations were precise, but no experiment could detect something curled smaller than an atom. The world moved on while the idea slept in the dark, like a fossil buried beneath future discoveries. But hidden ideas have a way of resurfacing when the universe changes the questions we ask. As the 20th century evolved, physics faced a crisis. Quantum mechanics explained the behavior of particles with astonishing accuracy. Einstein's theory of general relativity described gravity and the bending of space-time. Yet the two frameworks could not talk to each other. They were like two majestic structures built from different materials, each one sound and solid, but impossible to merge into a single building. Relativity ruled the cosmic scale of planets and galaxies. Quantum mechanics ruled the tiny world of atoms and particles. Whenever physicists tried to combine the two, the mathematics exploded into nonsense. Nature was supposed to be unified, but our equations were not. Something was missing. The search for that missing piece led physicists to a profound realization. Every attempt to unify the forces of nature kept pointing toward one solution. Not a new particle, not a new field, a new dimension, hidden geometry. Suddenly, the old idea of Kaluza and Klein was not a curiosity, it was a key. The more scientists explored quantum theory, the more the universe began to look like an arrangement of possibilities. Particles did not exist in one place until you measured them. Forces were not invisible pulls. They were exchanges of tiny packets of energy called bosons. Electromagnetism could be described by particles called photons, the weak nuclear force by particles called W and Z bosons, the strong nuclear force by particles called gluons. Everything seemed to reduce to particles and fields, but gravity refused to play along. If gravity were a quantum force like the others, it should be carried by a particle called the graviton, a particle that mediates the bending of space-time the way photons mediate electromagnetic interactions. But the graviton has never been detected, and if it exists, it behaves unlike any other particle. It couples to everything. It cannot be screened or blocked. It flows through matter, through emptiness, through entire galaxies, as if nothing can stop it. that strange behavior led to a daring thought. Maybe gravity feels different, because gravity does not live entirely in our four-dimensional space-time. Maybe gravity belongs to a deeper realm and only touches our universe, like a whisper from another direction. The first time that thought appeared in print, it seemed unbelievable, yet the mathematics continue to support it. The weakness of gravity could be explained if gravity spreads through more dimensions than the other forces. If light and electricity are confined to the four-dimensional surface of our universe, but gravity is free to wander through hidden directions, then of course, it would appear weak. We would be measuring only the tiny fraction that remains here. The rest would be flowing somewhere we cannot follow. Physicists began writing equations that described our universe as a kind of membrane. They called it a brane, short for membrane. The brane exists inside a larger arena called the bulk. Inside this picture, all matter and forces are stuck on the brane. Only gravity can explore the bulk. We move through our three space dimensions and through time, unaware that just beyond the thin skin of our universe, more directions stretch into something vast and silent. The idea was not fantasy. It came directly from the mathematics of extra dimensions. Kaluza and Klein had shown that one hidden direction could unify gravity and electromagnetism. Later theories suggested that more dimensions could unify all forces. Nature was trying to tell us something. Geometry is the blueprint of reality. The forces we observe are not fundamental. They are shadows cast by the shape of dimensions too small to see. This realization changed physics permanently. The world of science began to approach the fifth dimension, not as imagination, but as a question of evidence. Could we detect the effects of hidden dimensions, even if we cannot see them? Could particles behave differently if they were able to slip into the fifth direction? Could energy vanish from our detectors and appear to be missing, when in truth, it had simply moved into the curled space beneath space-time? These questions were not philosophical. They could be tested. When the Large Hadron Collider was designed, one of its goals was to search for signatures of missing energy, not lost data, not experimental error. Energy that vanished because it escaped into a direction we cannot access. If such a signal were ever found, it would be the first physical proof that the universe contains more than four dimensions. The possibility is breathtaking. Imagine a particle collision in which matter suddenly disappears, not through annihilation, but through movement. Not into a vacuum, but into another direction. That disappearance would not violate physics. It would reveal that our understanding of space-time was incomplete. And all of this began because one quiet mathematician decided to add a single new coordinate to Einstein's equation. A single symbol on a page that changed everything. Kaluza never witnessed how deep his insight would reach. Klein only caught a glimpse. Today, entire fields of physics descend from their idea. String theory, brane cosmology, quantum gravity. They all trace back to a moment in the 1920s when a new dimension entered the story of science. Humanity believes it has seen the world, but perhaps we have seen only the surface of a deeper architecture. The equations of physics suggest that we live in a universe shaped by directions we will never walk and spaces we will never touch. Yet those spaces shape us. They determine the forces that hold atoms together. They determine the behavior of light. They determine the structure of reality. We are not trapped in three space directions because those are the only ones that exist. We are trapped in three space directions because those are the only ones we can perceive. And somewhere, curled beneath every point in space-time, a fifth direction waits. Picture a thread stretched across a table. From your distance, it looks like a single line. One direction, forward or backward. But imagine shrinking until your size is smaller than a grain of dust, smaller than a cell, smaller than an atom. You would discover something astonishing. The thread is not one-dimensional. It has thickness. You could walk around it, circling its surface in a new direction that was invisible from afar. The dimension was always there. You simply lacked the scale to notice. Our universe may be exactly like that thread. For centuries, humans believed that space had only three directions: length, width, height. We built maps and cities and entire civilizations inside that assumption. The world felt settled, complete. But nothing about our senses guarantees truth. Human eyes can detect only a thin slice of the electromagnetic spectrum. Human ears can hear only a small range of vibration. And the human brain can imagine only what evolution required it to imagine. We were never meant to think about dimensions. A house cat does not ponder calculus. A butterfly does not consider the curvature of space-time. Humans evolved to throw spears and recognize predators hiding in tall grass. Our ancestors survived because they noticed patterns at the scale of trees and rivers. They never needed to detect a dimension curled smaller than a proton. Our senses are not tuned to reality. They are tuned to survival. Hidden dimensions would exist, whether we notice them or not. Imagine placing a pencil on a sheet of paper. An ant crawling on that paper sees only two directions: forward and sideways. The ant does not see the third direction rising above its world: upward. That direction exists, but the ant never uses it. It was born inside a smaller reality. The strange possibility is that we are the ant. We walk forward and backward. We move left and right. We climb up or down. We accept these three spatial directions without question because we experience them. We move through time because we are carried through it. But our lack of access to a fifth direction does not prove it does not exist. It only proves that we are confined. One question defines this chapter. If a hidden dimension exists, why can we not see it? The answer is scale. A dimension can exist without stretching outward like a corridor. It can be wrapped inward like a circle so small that no particle we have ever seen possesses enough energy to reveal it. This is the idea of compactification, the insight that Oscar Klein realized after reading Theodore Kaluza's work. The fifth dimension could be real, but curled into a loop at each point in space-time. Every location in the universe could contain that hidden direction. The universe would not be larger in a visible way. It would be deeper. The scale of this loop is not simply tiny. It is near the Planck length, the smallest meaningful measurement that physics can describe. The Planck length is not a unit like a meter or a kilometer. It is a boundary. It is the scale at which the very concept of distance begins to break down. If you tried to measure space below this scale, the fabric of reality would begin to fluctuate like a stormy sea of quantum uncertainty. Space would lose its meaning. To understand how small that is, imagine shrinking the diameter of a proton into a million smaller pieces. Even then, you would still need to shrink each of those pieces into another million. The hidden dimension would still be smaller. This is why we cannot see it. To detect a curled dimension, you must probe space with energy so intense that space-time itself vibrates. We would need a particle accelerator not the size of a building or a city or even a continent. We would need one stretching nearly the size of a solar system. Humanity is nowhere near that capability. We have barely begun to understand how to bend gravity, let alone how to reveal hidden directions. Compactification is not a poetic idea. It is a mathematical necessity. The equations that describe particles in a curled dimension produce quantized vibrational states. Those vibrational patterns determine the mass and charge of particles, like notes on a violin string. A different shape of the curled dimension produces a different pattern of vibration. The universe behaves not like a structure made of particles, but like a structure made of music. Each particle is a note. The hidden dimension is the instrument. There is something beautiful and humbling in this idea. The properties of matter do not exist because nature chose them. They exist because geometry demands them. Yet, even as the mathematics glows with elegance, our world remains stubbornly silent. We cannot see the curled dimension. We cannot access it, not with our hands, not with our eyes, not with the greatest tools we have ever built. We live our lives on the surface of reality like sailors crossing an ocean without knowing its depth. Imagine a creature living on the surface of a lake. It sees ripples beneath its feet and assumes the water ends there. It never imagines that the lake has depth. It never considers that entire ecosystems live below its world. Fish swim in a direction that the surface creature cannot follow. The surface world is real. The underwater world is also real. But the surface creature has no access to it. We may be surface creatures. The fourth dimension of time already reminds us that perception is not freedom. We do not walk backward through yesterday. We do not leap ahead into tomorrow. Time is a direction, and yet we cannot roam through it the way a bird roams through the sky. Our awareness of time does not give us control of time. Likewise, our inability to move into a fifth dimension does not prove that it does not exist. Physics teaches that existence does not require permission from human senses. And so the idea of compact hidden dimensions remains one of the most profound possibilities in science. We do not ignore them because we lack evidence. We study them because our mathematics demands them. The more deeply physicists study the universe, the more evidence they find that the world we experience is not the world that exists. Our senses evolved for survival, not truth. The reason we find extra dimensions strange is because our brains are built to understand motion on the scale of running across a field or climbing a staircase. But reality plays out on scales far beyond instinct. At the smallest scales, particles behave in ways that defy common sense. A particle can exist in two states at once. It can vanish from one location and appear in another without crossing the space in between. It can pass through barriers without breaking them, as if the barrier were not there. This is quantum tunneling, a phenomenon verified in laboratories countless times. When a particle tunnels, it behaves as though it slipped into another possibility, another path invisible to us. Some physicists wonder whether quantum tunneling is a hint that particles can move through dimensions we cannot see. The idea feels radical only because we are used to thinking of space as a flat stage. But what if space is layered? What if what we call here and what we call there are not separated only by distance, but by dimensional folds too small to perceive? When a particle disappears from one known point and reappears somewhere else, perhaps it has taken a shortcut through the curled dimension. We observe the beginning and the end. We miss the path. When we talk about extra dimensions, we often imagine something enormous, like a science fiction portal or a tunnel to a parallel world. But the universe speaks through subtlety, not spectacle. The fifth dimension, if it exists, would not be a hallway you could walk through. It would be like a circle smaller than the smallest imaginable measurement. If you tried to enter that circle, your direction of motion would simply bring you back to where you began. It would feel like no movement at all, because the dimension is closed on itself. You would never leave. You would only loop. This is why the fifth dimension is called compact. Not short, not hidden behind a curtain, folded inward into a tiny loop at every point in space. The loop does not exist far away. It exists here, everywhere, woven into the fabric of reality. The strangest part is this. If the curled dimension were only slightly larger, just a few orders of magnitude larger, the universe would behave differently. Photons would have different energies. Atoms would have different sizes. Stars might never ignite. The shape and size of the hidden dimension determines the laws of physics. We are accustomed to thinking of physical laws as fixed, eternal, engraved into nature. But what if they are the result of geometry? What if the laws of physics are simply what happens when matter moves inside a universe shaped by hidden dimensions? In this picture, the universe is not governed by laws. The universe is governed by shape. Imagine touching a guitar string. The note it produces depends on the length of the string, its thickness, and how tightly it is pulled. The universe might be the same. The particles that make up matter might be vibrations on the curled dimension. Change the shape of the dimension and the vibration changes. Change the vibration and the particle changes. Change the particle and the universe changes. Geometry becomes destiny. One of the most compelling pieces of indirect evidence for compact dimensions comes from a phenomenon called quantization. When particles move through a curled space, their motion cannot take on just any value. It becomes quantized, allowed only in certain discrete states, like a bead on a necklace that can only sit at certain fixed positions along the thread. In the 1920s, physicists discovered that electrons around a nucleus could only exist at certain energy levels. That discovery birthed quantum mechanics. But another interpretation is that the electron energy levels arise because electrons interact with hidden geometry. The universe may be quantized because space itself is quantized. Consider this comparison. A violin string cannot produce any random tone. It produces tones that depend on the length of the string and the number of half wavelengths that fit between its ends. Likewise, a particle moving around a curled dimension cannot adopt any state. It must choose specific vibrational patterns that fit evenly into the loop. Those patterns become the observable properties of the particle, such as mass and energy. It is not mystical, it is mathematical. However, this leads to a challenge. If the curled dimension is so tiny and so inaccessible, how do we test the idea? Science moves not on imagination, but evidence. A theory must leave fingerprints, even if those fingerprints are faint. Compact dimensions produce a prediction. If they exist, particles should sometimes behave as if they gain mass when moving through the hidden loop. They should adopt higher vibrational states. Those states should reveal themselves as what physicists call Kaluza-Klein modes, particles that are identical to known particles but heavier, because they are vibrating not only in the familiar three directions of space, but also in the hidden circumference of the compact dimension. These heavier states are not fantasy. They are predicted by mathematics. If we ever detect them in a collider, we will know that a dimension beyond the visible exists. This raises a new problem. To detect a hidden dimension, a particle must contain enough energy to vibrate into that curled direction. The energy required is near the Planck energy, a value so enormous that even converting the total mass of a mountain into pure energy would barely approach it. This is why hidden dimensions remain elusive. They do not hide because they are far away. They hide because they are extremely small. The universe does not reveal its architecture easily. To see the hidden dimension, we need a magnifying glass made of energy. Our best magnifying glass is the Large Hadron Collider. It accelerates particles until they reach nearly the speed of light, then smashes them together. In those collisions, space-time stretches and shudders. For an instant, the universe becomes like it was in the first moments after the Big Bang. Whenever that happens, there is a chance that a particle will slip into the curled dimension. If it does, the detectors will not see a new particle. They will see missing energy, a tiny, unexplained absence. Absence can be proof. When a collision produces less energy than expected, and every known interaction has been ruled out, the remaining explanation may be movement into a hidden dimension. Scientists are already searching for these signatures. They record millions upon millions of collisions every second. Most look ordinary. But one day, one collision may behave differently. One day, the universe may leave a fingerprint. We may observe not what enters the curled dimension, but what leaves us. The search for hidden dimensions is not only a scientific quest, it is a philosophical mirror. It forces us to ask whether our senses reveal reality, or whether they reveal only a projection shaped by our biology. When you look around, you see three dimensions, but you also see the horizon as flat, even though the Earth is curved. You see the stars as pinpoints, even though many are larger than the sun by factors of hundreds. Your senses show you only a sliver of what exists. The universe does not announce its full structure. It hides it behind scale, behind energy, behind the limits of perception. The compact dimension that Kaluza and Klein imagined is not somewhere else. It is here, everywhere. If you hold an empty cup in your hand, that cup is filled with billions upon billions of points in space, and at each point, the curled dimension exists. Every atom in the cup contains this hidden loop. Every point in the air you breathe contains it. The fifth dimension is not a distant place. It is the unseen architecture beneath every place. Think about that for a moment. At every location in the universe, reality may include a direction that no living creature can yet travel. We move through length, width, and height without effort. We advance through time without choice. But if there is a fifth direction, we do not move through it at all. We are pinned to our slice of reality, like paint on a canvas. The canvas might have depth, folds, hidden layers, but we experience only the surface. Every force we know, except gravity, appears to be bound to our slice. Light cannot leave our dimension. Electricity cannot wander into the hidden loop, but gravity might. Gravity may be the only force that touches the deeper structure of space-time. When physicists imagine gravity spilling into a hidden direction, they are not fantasizing. They are following mathematics that naturally arises from the equations. Imagine water falling onto a flat surface. The water spreads in every available direction. If you tilt that surface and attach a hidden slope, the water would spill down the hidden direction. Gravity may behave the same way. Our three-dimensional space and one-time direction are not the only directions where curvature can flow. If a curled dimension exists, gravity spreads into it, weakening the pull we observe. This is why gravity is so weak compared to electromagnetism. Gravity is not weak, it is diluted. The weakness of gravity may be the strongest evidence of all. If all space-time contained only the visible directions, then gravity should be as strong as the other forces. The universe would collapse into a soup of particles with no stars and no life. The only way to reconcile gravity with what we see is to accept that much of it escapes us. We feel only the leftover fraction that remains on our dimensional surface. Some of the greatest breakthroughs in science happen when we stop asking what we expect and start asking what the universe insists upon. The universe insists that gravity behaves strangely. It insists that space is curved. It insists that particles have quantized energy. It insists that most of the matter in the cosmos is invisible. When one idea speaks to several mysteries at once, science pays attention. Hidden dimensions answer more than one question. They answer many. They explain why gravity is weak. They explain why quantum particles behave as if they vibrate in discrete states. They explain why the laws of nature are so finely tuned that life is even possible. When we think of extra dimensions, we imagine alternate worlds. But the deepest truth might be simpler. The extra dimension is not a place, it is a cause. A condition that shapes every law of physics, a boundary that defines what matter and energy may become. At the smallest scales, space-time is not smooth and continuous. It trembles with uncertainty. Quantum foam is the name physicists give to the roiling chaos that exists when you look deeply into reality. Distance loses meaning, time loses coherence. At that depth, the curled dimension is not hidden. It is fundamental. All particles are influenced by it. They respond to the inner structure of space-time, just as ripples on water respond to the shape of the riverbed. We live inside a universe that is not as it appears. The classical world of everyday experience is only a thin layer resting on top of a deeper world of geometry. That deeper world is not just stranger than we imagine. It is stranger than we are built to imagine. The human mind evolved to find berries in bushes and to build shelters against storms. It did not evolve to hold the concept of dimensions curled smaller than a Planck length. The fact that we can even conceive of this possibility is one of the greatest achievements of human thought. There is a moment in every scientific revolution when the world must decide whether it will trust its senses or trust the mathematics that reveal what lies beyond them. When Einstein proposed that space and time form a single fabric, people resisted. When quantum theory revealed that reality is probabilistic, not deterministic, people resisted. Now we stand at another moment of resistance. Dimensions we cannot see challenge our intuition, not because they are impossible, but because we are limited. Hidden does not mean non-existent. The curled dimension may hold the key to everything we do not yet understand. It may link gravity with quantum mechanics. It may explain dark matter. It may reveal that we are living on a membrane floating inside a much larger space. If this is true, then our entire universe is like a ripple on the surface of a boundless ocean. We are not exploring emptiness. We are exploring architecture. We are exploring the blueprint of space-time itself. When you feel the pull of gravity, you are feeling the curvature of dimensions you will never see. When you watch a beam of light bounce off a mirror, you are witnessing the influence of a hidden direction. When you look at the stars, you are watching the surface of reality, unaware of the depth beneath your feet. We are the ant on the paper. The universe is the page. The fifth dimension is the depth we cannot recognize. And this is where the next chapter begins. If compact dimensions exist, if matter reacts to them, if gravity spreads into them, then the next question becomes unavoidable. How do we build a universe from hidden geometry? Imagine standing on the edge of a vast desert at night, sand stretching in every direction, the sky above scattered with uncountable stars. You look upward and wonder how something so silent can hold so much motion. Galaxies spin, stars are born, worlds collide, everything in the universe moves, yet the laws that guide those motions are written in a language no human voice can speak. Beneath every orbit, beneath every photon, beneath every atom lies an invisible code, a blueprint not of matter, but of possibility. For centuries, we believed that the smallest unit of reality was the atom, then electrons and protons, then quarks and fields. But the journey inward did not end there. It continued until physicists discovered that matter may not be made of particles at all. Matter may be made of vibration. String theory does not begin with imagination. It begins with frustration. Gravity refuses to fit into quantum mechanics. Space-time refuses to be tamed by probability. Every force can be placed into a mathematical structure called the Standard Model, except gravity. Gravity behaves like a rebel. It is the only force that bends space-time instead of living inside it. When physicists try to force gravity into the quantum framework, the equations explode with infinities. Not beautiful infinities that represent possibility, but broken infinities that represent nonsense. At first, no one knew what to do with this problem. Then a group of physicists examined an equation that described the vibration of one-dimensional filaments. Not particles, strings. These strings were unimaginably small, smaller than the Planck length, smaller than anything the human mind can visualize. They would be so tiny that if an atom were enlarged to the size of the solar system, a single string inside that atom would be no larger than a tree. When physicists examined the behavior of these vibrating strings, something miraculous happened. The mathematics that refused to work for point particles suddenly came together with effortless harmony. Gravity emerged naturally from the vibrations of the string. The particle that carried gravity, called the graviton, was no longer forced into the equations. It appeared as a result. The universe whispered its structure. But the whisper came with a demand. The equations only worked if reality contained more than 4 dimensions. Not 4, not 5, 10, and in some versions, 11. At first, the idea felt absurd. Why should the universe require more dimensions than we experience? But the equations did not care about human intuition. They cared only about truth. The hidden dimensions were not vast open spaces. They were curled into shapes so tiny that they lived at every point in space-time, like microscopic origami. These shapes were not simple loops like Kaluza and Klein imagined. They were intricate structures with twists and folds and tunnels, shapes called Calabi-Yau manifolds. Imagine the curled dimension from the previous chapter, the tiny loop that Kaluza and Klein envisioned. Now imagine not one loop, but a labyrinth of curled directions. Each point in spacetime contains a compact geometric sculpture with many folds. A Calabi-Yau manifold does not just sit beneath reality, it sculpts reality. The shape of these curled dimensions determines what kind of vibrations the strings can have. The vibrations determine what kind of particles exist. The types of particles determine the forces that govern the universe. Everything we know, from the mass of electrons to the color of stars, emerges not from a decision, but from geometry. The universe is not built from things. It is built from shape. If the curled dimensions have a certain structure, electrons exist with a certain mass. If the dimensions take a different structure, electrons could be heavier or lighter, or might not exist at all. In one shape of hidden dimensions, the strong nuclear force may form. In another, the universe might expand too quickly for atoms to bind. If the geometry is not right, stars never ignite. If the geometry shifts by a tiny fraction, chemistry collapses. Life would never begin. The laws of physics are not laws. They are consequences. Every atom in your body exists because the hidden dimensions of space-time have the right shape. When a violin string vibrates, it produces different notes depending on its length, tension, and thickness. A single string can become a symphony if those parameters change. Likewise, the tiny, vibrating strings at the foundation of matter produce different particles depending on how the strings vibrate. Some vibrations produce quarks, others produce electrons, others produce the photon that carries light. Physics textbooks describe these as different particles, but string theory whispers a deeper truth. All particles are different notes on the same instrument. The universe is music, and the hidden dimensions are the shape of the instrument. Imagine holding a glass bottle. Tap it gently with your finger. You will hear a note. Now pour some water into it. Tap again. The note changes. The bottle has not changed shape, but the vibration path has. That is the essence of string theory. Tiny changes in the structure of hidden dimensions alter the vibrations that create particles. Tiny changes in vibration alter the universe. This is more than philosophy. It is prediction. The extra dimensions force the existence of Kaluza-Klein modes, heavier copies of known particles. If we ever detect such a particle, we will know that hidden dimensions are real. And if we do not detect them, the theory collapses. That is the power of science. A theory must be vulnerable to the universe. It must risk being wrong. String theory was not created to explain extra dimensions. Extra dimensions were discovered within the theory. The mathematics led the way. Physicists simply followed. But the story deepens. Because once strings exist, the universe stops being made of particles entirely. Instead, everything becomes information. A string is not a thing. It is an instruction, a vibration, a pattern. Strings are like tiny programs. The universe is their output. Reality becomes code written into the geometry of dimensions. In this view, space-time itself becomes dynamic. It bends, it stretches, it fluctuates. Gravity emerges not from a force, but from the shape of the playground where strings vibrate. And the strange behavior of quantum mechanics, where particles behave like smeared-out probabilities until observed, begins to make sense. A particle is not a particle. It is a vibration of information. It becomes concentrated only when forced to interact. Suddenly, the universe feels less like a machine and more like a thought. Some physicists resist this conclusion, not because it is unreasonable, but because it is frightening. If the universe is information, then what is doing the computing? Does reality require a deeper substrate, a deeper framework beyond strings? Or is the universe the deepest level of itself, a self-contained loop, a dimension curled inward, not only in space, but in meaning? String theory does not claim answers. It claims possibilities. It gives the universe room to be stranger than we imagine. The next question is unavoidable. If dimensions exist beyond our senses, how do we detect them? not mathematically, but physically. The fifth dimension might reveal itself in particle colliders, but the higher dimensions predicted by string theory might reveal themselves through gravity. Gravity is the only force that touches all dimensions. Gravity is the only force that leaks. Imagine dropping a pebble into a pond. Ripples spread along the surface, but some of the energy sinks into the water beneath. The surface ripples weaken because part of their motion leaves the surface. Gravity might behave like those ripples. It spreads not only through our visible dimensions, but into the hidden ones. When we feel gravity, we may be feeling only the leftover fraction that remains in our world. If we ever detect missing energy in a collider, energy that does not transform into light or particles, that will be the first physical evidence of hidden dimensions. Humanity may discover the fifth dimension not by seeing it, but by noticing what disappears into it. This is the transition. We leave the mathematics of vibration and enter the physics of leakage. If strings require dimensions, then gravity reveals them. The next chapter follows a theory that shook the scientific world, a theory that treats our universe not like a space, but like a membrane suspended in a higher dimensional ocean, a surface floating in a depth we cannot yet comprehend. Gravity is the most patient storyteller in the universe. It whispers instead of shouts. It bends instead of pushes. It does not flash or spark or light up the night sky like electricity. It does not bind atoms together like the strong nuclear force. It does not guide radioactive decay like the weak nuclear force. Gravity simply shapes everything. It sculpts the paths that planets follow around stars. It bends the light from distant galaxies. It pulls atoms together into clouds, clouds into stars, stars into galaxies, and galaxies into the grand structure of the cosmos. Yet for all of its power, gravity is also absurdly weak. A cheap refrigerator magnet can lift a paperclip and defeat the gravity of an entire planet. Something about that does not make sense. Imagine standing in a great hall filled with towering stone pillars. Each pillar represents one of the forces of nature. The strong nuclear force stands as a massive pillar carved from granite. It holds the atomic nucleus together with ferocious strength. Beside it stands the weak nuclear force, smaller, but still formidable. It governs the transformation of particles inside stars. Electromagnetism stands tall and elegant, shaping chemistry, technology, and every beam of light you have ever seen. And then there is gravity, a fragile pillar made of glass. Thin, delicate. It should be the most impressive structure in the room, yet it feels like the weakest. For decades, physicists tried to ignore that embarrassment, but eventually the universe forced them to ask the forbidden question. What if gravity is not weak? What if gravity is leaking? What if gravity is spreading into a hidden direction that we cannot see? If the world contains hidden dimensions, then gravity would not be confined to the four-dimensional surface of space-time. It would move outward. It would dilute. It would weaken. This is the heart of the Randall-Sundrum model, a revolutionary idea introduced in the final year before the new millennium. Lisa Randall and Raman Sundrum proposed that our universe might be a brane. Not brain, brane. A membrane like the surface of a soap bubble. Imagine that our entire universe is a thin sheet floating within a higher dimensional arena called the bulk. We live on the brane. Our entire reality is confined to it. Light cannot leave the brain. Electromagnetism cannot leave the brain. The particles that make chemistry and life possible cannot leave the brain. They are trapped on the surface like colors painted onto a canvas. Gravity is different. Gravity is not painted on the surface. Gravity is the shape of space-time itself. It is the bending of geometry. Because geometry does not care about boundaries, gravity can flow into the bulk. Picture a drum. When you strike the drum's surface, vibrations spread outward across the skin. But if the drum had depth, those vibrations might also pass into the interior. gravity may behave the same way. It begins on our brain, but it spreads into the deeper bulk. If that bulk contains a fifth dimension, then gravity will be strongest where the extra direction is shallow and weakest where the extra direction expands. The Randall-Sundrum model does not invent this structure. It allows the mathematics to decide. When they solved Einstein's equations inside 5 dimensions, the brane and the bulk emerged naturally. The model predicted that gravity is strong near certain regions of the bulk and weak on others. We live in the weak region. This is why gravity feels powerless compared to electromagnetism. We are standing on the edge of a cliff inside the bulk. Gravity rolls away from us into the deeper dimension. Consider a candle in a dark room. When the flame burns, light spreads in all directions. If the room were flat, the light would remain bright. But if there were an opening that led to a deeper darkness, some of the light would escape. It would fade. Gravity may be the candle. The fifth dimension may be the opening. For the first time, the weakness of gravity was not a defect. It was evidence. If our universe is a brane, then we are not the center of reality. We are the surface of something deeper. And gravity is the only force allowed to explore the depth. To imagine the brane, do not picture science fiction doors or portals. Picture a sheet of paper floating inside a room. A two-dimensional creature living on that sheet would know only 2 directions, forward and sideways. It would never imagine the third direction, up. We are those creatures. We have lived every moment of our lives on the surface of a 4-dimensional brane. We move forward and backward, left and right, up and down. We drift through time, carried along like rocks rolling in a river. We never notice the flow of gravity into the higher, dimensional bulk because we have no sense organ that can detect dimensional movement. The brane is where matter lives. The bulk is where gravity breathes. If this model is correct, then the universe is deeper than we perceive. The true arena of gravity is not our visible space-time. The true arena is the bulk. And every gravitational interaction we observe is only the shadow of a deeper geometric conversation. In the bulk, gravity flows freely. It spreads like smoke. But when gravity touches the brane, we feel only the faint remainder that is left behind. The Randall-Sundrum model describes something startling. Space is not uniform. The bulk is warped. It bends and stretches like a valley. Our universe is like a ledge along the wall of that valley. Gravity rolls down the slope into the deeper dimension. Suddenly, the universe is not a vast, open plain. It is a layered structure. In this picture, the Big Bang was not the beginning of all existence. It was the moment our brane formed. Perhaps 2 branes collided. Perhaps our brane pinched off from another region of the bulk. Perhaps branes merge and divide like soap bubbles drifting in air. If that is true, then there may be other branes all around us, universes parallel to our own, separated not by distance, but by dimensional direction. Other universes may be less than a centimeter away, but we will never meet them, because we cannot move in that direction. And yet, the one force that ignores boundaries might touch them. Gravity could pass from one brane to another through the bulk. This leads to an extraordinary possibility. What we call dark matter, the invisible mass that makes up nearly all of the universe, could be ordinary matter on a neighboring brane. When we observe gravitational pull from empty space, perhaps we are not observing emptiness. Perhaps we are observing another universe. Once again, the mathematics does not care whether humans find this strange. It only cares whether the equations work. And the equations work beautifully. The idea that gravity leaks into the 5th dimension leads to predictions that can be tested. One of those predictions concerns how gravity behaves at extremely small distances. If extra dimensions exist, gravity should become stronger when objects are brought closer than a fraction of a millimeter. Experiments have tested gravitational force at distances as small as 1/10 of a millimeter, and no deviation has yet been found. But the tests grow more sensitive every year. A fraction of a millimeter may still be too large. the fifth dimension could be hidden deeper than this. Another prediction appears in particle collisions. If gravity spreads into the bulk, then during a high-energy collision, some of the gravitational energy should vanish into the extra dimension. Physicists search for missing energy in collider experiments. If enough collisions show unexplained missing energy in patterns consistent with higher dimensional models, that would be our first direct evidence of the bulk. The most dramatic prediction involves microscopic black holes. If gravity becomes stronger at tiny scales due to hidden dimensions, then the Large Hadron Collider could create miniature black holes that evaporate instantly in a flash of radiation. The evaporation would produce a specific signature, a burst of energy followed by missing energy as gravity leaks into the bulk. As of today, no microscopic black hole has been detected, but the collider has not yet reached the energy levels required to probe deeply into the hidden dimension. Each upgrade brings us closer. Science is not driven by what is comfortable, it is driven by what is true. And the mathematics of higher dimensions keeps returning to the same conclusion. Gravity is not weak. We simply live in the wrong dimensional perspective to see its strength. The realization is unsettling. It means that our universe is not the whole theater of reality. It is only the stage surface. The actors on this stage, the particles and atoms and forces that build everything we know, dance across a two-dimensional surface of a deeper object. We see the costume. We never see the scaffolding. We are inside a world that touches something larger, and gravity is the only force that remembers. When you drop a stone and watch it fall, you are watching gravity move toward the fifth dimension. When galaxies rotate faster than visible matter allows, you are witnessing gravity interacting with mass beyond our brain. When space-time curves around massive stars, you are seeing the surface ripple of something happening in the depth. The weakness of gravity is not a flaw, it is a clue. The universe has been hinting for 100 years that we are missing a direction. Now the question becomes deeper. If the fifth dimension can hold mass, organize structure, and allow gravity to leak, then what else might live there? What if the dark matter haunting our universe is not something exotic? What if it is simply matter trapped on another brane? The next chapter follows that possibility. There is a moment in every scientific journey when the universe stops cooperating with what we expect. A moment when observations refuse to match belief. For astronomers, that moment arrived when they measured the rotation of galaxies. They stared at swirling islands of stars and saw something impossible. The stars at the edges of galaxies moved much too fast. According to Newtonian gravity and Einsteinian geometry, the outer stars should slow down. They should orbit lazily, while the inner stars whirl rapidly around the center. But the data said something else. The stars on the outskirts moved almost as fast as those near the core. It was as if an invisible hand was gripping the galaxies, holding them together, preventing them from flying apart. The universe was telling us that there is more mass than we can see. Scientists called this missing mass dark matter, not because it is mysterious, but because it does not interact with light. It does not absorb light. It does not emit light. It does not reflect light. Light passes through it indifferent. We can see the gravitational effects of dark matter, but not the matter itself. It leaves no trace on telescopes, no color, no shadow, only gravity. The first careful measurements came from galaxies in the 1930s, when astronomers expected elegant confirmation of Newton and Einstein. Instead, they discovered chaos. The stars behaved as if 95% of the mass was invisible. 95% of the universe is not ordinary matter, not atoms, not molecules, not stars, not planets, not you. The visible universe is just the foam on the surface of a deeper ocean. For decades, scientists searched for what dark matter might be. They imagined particles called WIMPs, weakly interacting massive particles. These particles would drift through ordinary matter without leaving a trace, passing through entire planets without striking a single atom. Experiments were built deep underground, shielded from cosmic rays, waiting for a dark matter particle to collide with something. None appeared. Year after year, detectors stayed silent. At some point, silence becomes a message. The universe was withholding something. The invisible mass behaved exactly like matter, yet refused to interact with anything except gravity. Why would matter hide from every force except gravity, unless it does not live in our dimension? This idea did not emerge from imagination. It emerged from necessity. If gravity can leak into a higher dimension, then matter confined to another brane could tug on our universe through gravity alone. Imagine two sheets of paper pressed together. Draw a dot on one sheet. The dot never touches the second sheet. The creatures on the second sheet never see the dot. But if the dot had mass, the two sheets would feel the slight pull. Only through gravity would they sense each other. Dark matter may be the gravitational fingerprint of matter on a neighboring brane. That idea began as a whisper in theoretical physics. Then the whisper became a hypothesis. Then the hypothesis became mathematics. Finally, the mathematics became testable predictions. If matter exists in a hidden dimension, then colliders like the Large Hadron Collider should occasionally produce particles that vanish. Not vanish through destruction, vanish by leaving our brane. This phenomenon is called missing energy. When two high-energy protons collide, every bit of mass and energy must be accounted for. The detectors measure every particle that emerges. But if a particle slips into the fifth dimension, the detector will record less energy than expected. Something disappeared. Not into nothing, but into somewhere. This is not fantasy. Detectors at the Large Hadron Collider are built specifically to search for missing energy events. Physicists study the debris of billions of collisions every second, searching for patterns where energy appears to be lost. If those losses align with predictions from higher dimensional models, then the missing energy would serve as evidence of a fifth dimension. So far, no definitive signature has emerged, but physicists are patient. Nature does not reveal itself on our schedule. Consider what dark matter does to galaxies. It surrounds each galaxy in a halo of invisible mass that binds the system together. Without that halo, galaxies would tear themselves apart. Dark matter flows not like gas or dust, but like structure. It forms cosmic highways connecting galaxies into filaments stretching across hundreds of millions of light years. When astronomers map those filaments, they are not mapping ordinary matter. They are mapping a gravitational landscape drawn by something unseen, a vast cosmic skeleton made of invisible mass. And here is where the fifth dimension leads to a radical thought. The pattern of dark matter looks like a shadow of something not in our universe. Picture two universes, two branes, floating in a higher dimensional bulk. Matter on one brane exerts gravitational influence on matter in the other. The branes do not touch, yet their gravity leaks through the bulk. The matter in the unseen brane would feel like missing mass in ours. We would never detect the particles. We would detect only gravity. Dark matter becomes an illusion of mass cast across a dimensional boundary. To visualize the idea, imagine holding two sheets of glass. You draw a picture on one sheet, but you look at the other. The pattern you see is not truly on the second sheet. It only appears there because of proximity and light. In the same way, we see dark matter not directly, but as the gravitational imprint of mass that exists in the hidden dimension. This idea explains the stubborn properties of dark matter. It does not scatter. It does not radiate. It does not slow down as ordinary matter does. It is not bothered by magnetic fields. It does not collide with itself. It behaves as if it is not made of particles at all, but of geometry. And geometry is exactly what the fifth dimension provides. Another clue lies in the cosmic microwave background, the faint afterglow of the Big Bang. When satellites observed the early universe with unimaginable precision, the data revealed that dark matter was already there from the beginning. It influenced the formation of the first structures. But dark matter and ordinary matter did not interact. They pass through one another like ghosts. If dark matter were ordinary matter, simply invisible, it would still collide, heat up, compress, and form dense clumps. Instead, it floats like a ghostly scaffold, ghostly matter, or matter on another Brane. Consider the elegance of this explanation. Instead of inventing new forces or new kinds of particles, dark matter could simply be normal matter that cannot cross dimensions. We feel its pull, but never see its light. The mathematics suggests that Kaluza-Klein particles may exist, heavier versions of known particles created when matter vibrates in the curled dimension. Detecting one of them would confirm the existence of compact dimensions and reveal the architecture of reality. These particles would appear only at energies far beyond those used in ordinary experiments. Only the most powerful collider ever built might glimpse one. Physicists do not chase proof because they want to be right. They chase proof because the universe deserves honesty. Imagine this scene. Two protons accelerate inside the Large Hadron Collider. They approach the speed of light. They collide. Energy erupts into a spray of particles, each traced through magnetic fields, each measured by sensors that fill an underground chamber as large as a cathedral. The detector logs the event. The energies do not add up. Something is missing. Something took energy elsewhere. Not into dust, not into heat, into a direction. Dark matter may not be an object. It may be a location. If a fifth dimension exists, then missing energy in colliders is not loss. It is movement. Energy has slipped away into a curled dimension, exactly as predicted. The moment this happens and is confirmed, humanity will have proved that reality contains more than 4 dimensions. We will no longer be living in speculation. We will be living in revelation. Until that day arrives, we stand in suspense. The universe hides more than it shows. When we look into the night sky, we see glowing matter, but that glowing matter is rare. The darkness between stars is not empty. It is filled with mass and structure we cannot see. Dark matter shapes the universe more than light ever has. Perhaps the most humbling truth is this: the universe we see is not the universe that exists. We live in a world where reality extends beyond our senses, where existence stretches into directions we cannot imagine, where gravity leaks into darkness, where matter may be trapped on another dimensional sheet, and someday soon, technology will grow strong enough to confirm or deny everything. We are close. The next question follows naturally. If dark matter might be the shadow of another dimension, then what else might reveal the presence of hidden geometry? Could we detect the fifth dimension directly? Could we create a moment where the wall between dimensions trembles? Colliders may find clues, but there is a more dramatic possibility. The ultimate test of hidden dimensions is to create a miniature black hole. To understand why, we move to the next chapter. Beneath the gentle hills of Switzerland and France, deeper than the roots of forests, beneath farmland and vineyards, a ring larger than many cities hides in silence. Most people pass over it unaware. They drive on roads above it. They walk their dogs above it. They sip coffee in small towns above it. Yet directly under their feet lies the most ambitious scientific instrument ever built, the Large Hadron Collider, a ring 27 kilometers around. It is a machine that pushes the laws of nature toward the point of fracture. A cathedral of magnets and vacuum and electric fields so precise that the slightest error would ruin the entire experiment. The Large Hadron Collider was not built to prove extra dimensions, yet the possibility that it might do so hangs over every run like a storm waiting to break open the sky. Inside that ring, protons race around at nearly the speed of light. They travel through a vacuum emptier than outer space. They rush between superconducting magnets chilled to temperatures colder than deep space itself. They circle the ring thousands of times each second, gaining energy with every lap. A proton inside the collider moves with such speed that if nothing stopped it, it could travel to the moon in a little over a second. Then, two beams traveling in opposite directions are guided into collision. Not gently, violently. Energies that once existed only in the first moments after the Big Bang are recreated in an underground tunnel. For a fraction of a fraction of a fraction of a second, space-time becomes liquid. In that moment, nature must reveal itself. When two protons collide, they do not hit like billiard balls. They break open. They release the quarks and gluons inside. The collision becomes a storm of particles flying in all directions, each one recorded by detectors the size of apartment buildings. Every fragment is measured. Every path is tracked. Every trace of energy is logged. Nothing escapes unnoticed, unless it leaves our dimension. Scientists do not search for hidden dimensions by looking for them. They search by counting energy. The law of conservation of energy states that energy can neither be created nor destroyed. It can only change form. If the energy measured after a collision is less than the energy put in, something has carried energy away. The detectors are built like an enormous three-dimensional trap. If a particle flies off, the trap records its path. If light is emitted, sensors record its wavelength. But if energy vanishes, if nothing appears in the detectors where something should appear, then there is only one explanation. Something exited the brain. In simpler terms, something left our universe. The hunt for extra dimensions is therefore a hunt for missing energy events. The detectors search for signature patterns, jets of particles on one side of the collision chamber with nothing on the other. Energy balance sheets that do not add up. Physicists examine these patterns one collision at a time, like detectives searching a crime scene. They eliminate every possible normal explanation: detector fault, noise, known particle behavior. Only when all familiar explanations are ruled out does the extraordinary remain. The first time such an event occurs with confidence, humanity will know that space contains more directions than we can travel. But missing energy is not the only sign of extra dimensions. There is another possibility, a possibility so dramatic that science once believed it belonged to fiction. If extra dimensions exist and gravity strengthens at tiny scales, then a collider could create miniature black holes. Not black holes large enough to swallow cities, not even large enough to swallow a proton. These black holes would exist for an unimaginably short time, then evaporate instantly. To understand how ridiculous that sounds, imagine compressing a mountain into a volume smaller than an atom. Now imagine doing that with two protons. That is what the collider attempts. Black holes form when mass compresses into an intensely small volume. In our four-dimensional universe, you need enormous mass to create a black hole. But in a universe with extra dimensions, gravity behaves differently. It concentrates more easily. Instead of spreading over 3 dimensions of space, gravity can focus into the hidden direction. The mathematics of the Randall-Sundrum model shows that if the 5th dimension exists, gravity becomes far stronger at tiny distances. It grows rapidly as objects approach one another, eventually becoming powerful enough to create miniature black holes from microscopic collisions. The Large Hadron Collider has not yet reached the energy required to cross that threshold, but it is close. Each upgrade pushes the machine closer to discovering whether our universe leaks into something deeper. Physicists can predict exactly how a miniature black hole would decay. According to quantum physics, black holes emit radiation as they evaporate, a phenomenon called Hawking radiation. A microscopic black hole created in a collider would evaporate almost immediately, releasing a burst of energy into the detectors. The signature of this burst would be unmistakable, a sudden flash of particles of many types, all radiating from a single point, followed by missing energy as gravity pulls the last fraction of the black hole into the hidden dimension. That pattern is the smoking gun of extra dimensions. No flash, no signature, no missing energy, and the hypothesis weakens. A flash with the correct signature, and centuries of philosophy transform into physics. A 5th dimension steps from speculation into reality. To understand the scale of what these experiments attempt, consider this. The amount of energy required to probe distances near the Planck length is enormous. If you converted the mass of an entire mountain into pure energy, the burst would still be too weak to observe the geometry of hidden dimensions directly. Yet the collider takes the mass of 2 protons, accelerates them to tremendous speeds, and concentrates their energy into a space smaller than the proton itself. For an instant, a portal opens to the deepest architecture of reality. The particles do not move through it, but energy does. The collider does not destroy matter. It reveals possibility. Even if miniature black holes never appear, the collider can still reveal extra dimensions by detecting Kaluza-Klein particles. These are heavier versions of known particles, created when a particle vibrates in the hidden dimension. In ordinary 3-dimensional motion, a particle might move forward, backward, left, right, up, and down. But if a curled dimension exists, the particle can move in that direction as well. That movement would appear as additional mass. A Kaluza-Klein particle would behave exactly like an ordinary particle, but it would weigh more. It would be the same fundamental object vibrating in a deeper direction. If the collider detects a particle identical to an electron but heavier, or identical to a photon but heavier, then hidden dimensions are not theory, they are fact. In the control room of the collider, physicists sit around glowing screens. They speak softly, they run tests, they examine data. They know that what they are searching for may never be found. They also know that if it is found, everything will change. Sometimes, in the middle of a run, the team pauses to watch a simulation of the machine. A glowing ring, a pulse of light racing around it, faster and faster until it becomes a blur, then 2 blurs colliding. Inside that blur may lie the doorway to another dimension. The collider was not built for comfort. It was built for truth. Even now, the machine prepares for future updates. New magnets, higher energy beams, better detectors. Each upgrade sharpens its vision. Each increase in energy pushes deeper into the geometry of space-time. Science knows that even if this collider finds nothing, future machines will go further. One day, there will be a collider not 27 kilometers long but 50 kilometers long, then 100, then perhaps a collider that surrounds the moon. Humanity advances by scaling curiosity. There is something poetic in the fact that the largest machine humans ever built exists to study the smallest structures that have ever been imagined. We build tunnels underground to find dimensions above us. We accelerate tiny particles to glimpse infinite space. We break matter to understand reality, and woven through every collision is a single question. What if our universe is not the whole universe? Imagine this possibility. 2 protons collide, energy explodes, a fraction vanishes. A detector records nothing where something should be. A scientist stares at the data. Her hands tremble. She checks again. No error, no miscount. The universe has lost energy, but energy cannot be lost. It can only move into a direction we cannot follow. The discovery of a 5th dimension would not merely rewrite physics. It would redefine existence. It would prove that our universe is not alone. That reality extends beyond the visible. That the surface we call space-time is not the whole canvas, only the part we are allowed to touch. When the first missing energy event is confirmed, humanity will know this truth. We are living in a universe with depth. The collider is not searching for particles. It is searching for the rest of reality. And the next step leads to an even more astonishing thought. If dimensions exist and branes exist, then perhaps our universe began not from nothing, but from collision. There is a moment when every field of science confronts a truth so uncomfortable that it forces a change not only in theory, but in imagination. Cosmology faced that moment when scientists traced the universe backward in time. If you reverse the expansion of galaxies, if you compress the stars and the dust and the space between them, everything converges to a single point, a moment when the universe was infinitely dense and unimaginably hot. That moment is called the Big Bang. For nearly a century, the Big Bang has stood as the accepted origin of everything. Time itself begins there. Space emerges there. all matter, all energy, every atom that would become every star and every life form begins in a single blinding instant. But the Big Bang theory contains a wound. It explains what happened after the beginning. It does not explain the beginning itself. It gives us no cause. It gives us no why. It gives us no before. The moment before the Big Bang, the moment that would hold the reason, is sealed from view by a wall of infinite density. At that moment, the laws of physics stop working. The equations break. Reality refuses to reveal what came before. The universe becomes a sealed book with its first page glued shut. For decades, scientists accepted this limit with frustration. A singularity, they said, an origin beyond reach. We cannot look past the first fraction of a second because the mathematics will not allow it. That limitation remained until the arrival of ideas from higher dimensional physics. When physicists began treating the universe not as a standalone container but as a surface inside a larger dimensional space, everything changed. In Brane world theory, the Big Bang is not the beginning of everything. It is the beginning of our brain. Imagine two enormous sheets of flexible space floating inside a higher dimensional bulk. These sheets are not metaphorical. They are physical surfaces. Each sheet is a universe. Each one contains its own matter, its own stars, its own time. The sheets float, bend, ripple, and over unimaginably long periods, drift through the higher dimensional space. On one sheet is our universe. On the other may be another universe, completely separate but existing only one-dimensional step away. Now imagine these two brains drifting slowly toward each other. For billions of years they approach. They do not collide quickly. They slide. They stretch. They warp the bulk through their gravity. And then, at some moment, they touch. That moment is the Big Bang. In the ekpyrotic model, developed in the early years of the new millennium, our universe did not begin as an explosion from nothing. It began as a release of energy from a collision between brains. The energy of impact transformed into the heat of creation. Space inflated outward. Matter condensed. Time began moving forward from that instant. The universe was born not from emptiness, but from contact. The word ekpyrotic comes from an ancient concept meaning born from fire. Yet here the fire is not myth, it is geometry. When brains collide, the kinetic energy trapped in their motion converts into radiation. The temperature at that moment reaches values beyond ordinary comprehension. Every point of space we now observe was once compressed into that contact region. Every galaxy, every atom, every future life was encoded in that initial flash. Once the collision passes, the brains recoil and begin drifting apart again, carrying with them the expanding universes they contain. This model addresses one of the most puzzling problems of classical cosmology. In the standard Big Bang model, the early universe expanded evenly in all directions, an astonishing uniformity that has always seemed improbable. Why should every region of the universe, separated by vast distances, share the same temperature? In the Brane collision model, this uniformity is natural. When brains collide, the entire impact region shares the same temperature before expansion begins. When the universes inflate, they expand from a common thermal event. The smoothness of the cosmos is not an accident, it is a scar left by the collision. Consider how profoundly this shifts our perspective. The Big Bang is no longer a singular event erupting from nothingness. It is an exchange of momentum between universes. The energy that became matter was not summoned from void, it was freed from motion. Just as two waves in the ocean can combine their motion into a moment of towering force, two brains can convert their kinetic energy into the birth of a universe. The moment of impact becomes our beginning. The rebound becomes our expansion. The separation becomes our time. In this view, time did not begin with the Big Bang. Time existed already in the bulk. The brains were moving long before the collision. Time flowed in the higher dimensional space, even while our brain did not yet exist. This means something extraordinary. There was a before our universe, before our time, before space-time as we know it. The collision of branes gives the universe a history beyond the Big Bang, not a supernatural cause, a physical one. The universe does not spring from nothing. It emerges from interaction. The ekpyrotic model also explains another mystery that has long haunted cosmology. Quantum fluctuations in the early universe seeded the galaxies we observe today. In the traditional Big Bang picture, these fluctuations are random. They appear without cause. But in the Brane collision story, those fluctuations arise from the wrinkles of the branes themselves. Picture sheets of fabric rippling as they approach. Those ripples leave imprints on the newborn universe. The structure of space-time becomes a record of the shape of the branes at the moment of contact. Imagine touching a mirror covered with dust. Your fingerprint leaves a perfect pattern. The first galaxies were formed from those fingerprints. Suddenly, the origin of structure in the universe is no longer mysterious. It is memory. Space-time remembers the wrinkles of the brane. The galaxies are written into existence by the geometry of the collision. There is something poetic in that. The universe we observe is not simply expanding, it is unfolding. This model also suggests an astonishing possibility. If branes can collide once, they can collide again. The expansion of the universe is not a one-time event. It may be part of a cycle. Branes drift. They collide. A universe is born. They drift apart. They drift back. A new collision. A new universe. Time may not be a line. Time may be a loop. Even more unsettling is what this model implies about dark energy, the force that accelerates the expansion of the universe. Instead of dark energy being a mysterious property of empty space, it could be the result of the tension between branes. Like two magnets pulled apart, the branes store potential energy in their separation. That tension stretches the branes, driving expansion. The universe expands because the branes are under strain. Every star we have ever seen, every planet, every choice, every life may exist because two universes brushed against each other in a higher dimensional night. The idea sounds almost mythical, yet it arises directly from mathematics. It is not wishful interpretation, it is geometry expressed as physics. The Brane collision model is not proven, it may be wrong, but it offers answers that the traditional Big Bang cannot. It explains uniformity, it explains structure, it explains dark energy, it gives us a before, it gives us a cause, and most important, it gives us a way to test the idea. If our universe began in a Brane collision, then gravitational waves should carry signatures of that event. The early universe should contain patterns in the cosmic microwave background that correspond not to a spontaneous explosion, but to a directional impact. Scientists are searching for these patterns now. The data is not yet definitive, but hints exist, swirls, alignments, anomalies that should not be there in a purely random inflationary expansion. It may take decades, it may take a new generation of telescopes, but someday we may detect the echo of another universe. If that day comes, it will rewrite the human story. We will no longer live in a universe that came from nothing. We will live in a universe that came from contact. The universe will become part of a larger ancestry, a genealogy of worlds. Imagine finding ancient carvings beneath layers of paint. You thought you were looking at the original artwork. Then the paint cracks and another layer appears. Another story, another history. The Brane collision theory peels back the first layer of our cosmic story. It suggests that our universe is not the painting. It is one stroke of color on a much larger canvas. If branes exist, then we are not the center of reality. We are the surface of a deeper structure. The next chapter asks a dangerous question. If dimensions exist beyond perception, and if our universe is a brane, then what does that make us? Are we confined beings trapped on a cosmic sheet? Is reality vaster than we can ever travel, and more frightening than that? If there are other brains, are there other versions of existence? Close your eyes and imagine holding a sheet of paper. Now imagine drawing a small dot somewhere near the center. To you, as a three-dimensional being, the dot sits on the surface. You can lift the sheet, bend it, fold it, twist it. The dot does not feel the motion. The dot does not know that you exist. To the dot, only the two-dimensional surface is real. Movement toward you is impossible. Movement away from you is impossible. The entire universe of the dot is flat. That is us. According to Brane world physics, our universe is not the void. It is not the whole. It is a surface. A four-dimensional membrane floating in a higher dimensional bulk. We are not suspended in space. We are embedded in a spatial sheet. Everything we know exists on that sheet. Every galaxy, every star, every atom, every law of physics. When we look at the night sky, we are not looking into the universe. We are looking across the universe. What lies beyond the sheet is not emptiness. It is direction. We call it the fifth dimension, not metaphorical, literal. To move into the fifth dimension is not to travel to another place. It is to travel off of the sheet entirely. We are trapped on the Brane, not because of some cosmic prison, but because the forces that hold matter together are Brane-bound. The electromagnetic force that shapes atoms and molecules is trapped to the Brane. The strong nuclear force that binds protons and neutrons is trapped to the Brane. Even the weak nuclear force that guides radioactive decay is trapped. Only gravity leaks. This is the key that makes Brane world theory testable. If gravity can spread into the fifth dimension, then on our Brane it appears weaker. That is exactly what we observe. Gravity is unimaginably weak compared to the electromagnetic force. If you lift a paperclip with a small magnet, that tiny magnet defeats the gravitational pull of the entire planet Earth. That imbalance is absurd in three-dimensional physics, but in Brane world physics, it is expected. Gravity seems weak, not because it is weak, but because we are not receiving all of it. Imagine two people talking through a thick wall. The sound is muffled, not because the speaker is whispering, but because the sound spreads through other rooms. In the same way, gravity spreads into directions we cannot access. We feel only what remains. The geometry of our universe shapes what we can perceive. A fish that lives its entire life at the bottom of the ocean might see the surface only as a shimmering boundary. It might never imagine that above that surface lies air, or land, or stars. That is us in relation to higher dimensions. We observe the cosmic microwave background. We measure galaxy rotation. We map gravitational waves. Yet everything we observe is data from the same sheet. We have never seen the bulk. We have only felt it through gravity. Some models suggest that distances in the fifth dimension might be microscopic, curled into tiny loops so small that even light cannot fully enter them. Other models propose something far more dramatic. The fifth dimension might be enormous, perhaps infinitely large, while our Brane is thin and stretched like a film. If true, the space beyond our universe is not small, it is vast. We may be the flat ones. Imagine this. Our Brane ripples like the surface of a pond. Every gravitational wave detected by our instruments might not simply travel across the universe, but into the bulk, waves of space-time leaking into deeper space. When the first gravitational wave was measured in the year 2015, detectors heard a faint chirp, the echo of two distant black holes colliding. But what if that chirp also carried information from another dimension? What if only a fraction of the wave reached us? There is a thought that keeps many physicists awake at night. If we are a Brane, then our universe might have neighbors. Other Branes could float parallel to ours just a small dimensional distance away. They might be similar. They might be utterly alien. They might even have their own versions of physics. If matter on their Brane gravitates, we could feel its pull. We might mistake it for dark matter. Some scientists quietly wonder whether the large-scale structure of dark matter halos could be shaped not only by matter in our universe, but by matter in a neighboring universe that exerts gravitational pull through the bulk. Dark matter might not just be an unseen particle, it might be an unseen world. Yet, even if there are other branes, movement between them is forbidden. We cannot leave our brain. We cannot even lean into the direction of the fifth dimension. The forces binding us are unbreakable. Imagine trying to step outside the surface of a mirror. No matter how much force you apply, you cannot walk into the reflection. It is not a place. It is a dimension of confinement. Every atom you have ever touched, every memory you have ever formed, every moment you have ever lived, took place within the surface of the brain. Even your thoughts are brain-bound. When you imagine distance, you imagine 3 dimensions. When you imagine time, you imagine one direction. You do not instinctively imagine space beyond space. Dimensions shape cognition. If we had evolved with access to 5 spatial directions, our intuition would be different. We would be able to imagine movement not only forward, backward, left, right, up, down, but also into and out of the brain. But we cannot. Our minds have been sculpted by confinement. The idea that we live on a membrane challenges something deeper than physics. It challenges identity. If our universe is a surface, then what does that make existence? Are we real, or are we a projection of something more fundamental? If 95% of the mass in the universe is hidden from us, and if gravity leaks, then what we see may be only the shadow of the bulk. The idea is uncomfortable because it shrinks our importance. For thousands of years, humans believed they lived at the center of everything. First, the center of the world, then the center of the solar system, then the center of the galaxy, then the center of the universe. Each discovery removed us from the center. The fifth dimension removes us from the universe entirely. We are not the center, we are the surface. Yet there is a profound beauty in this realization. If our universe is a brain, then existence is far larger than we thought. Reality is not a box, it is a stack of worlds, a layered architecture of dimensional surfaces. Somewhere beyond the thickness of our brain, another universe may be drifting. Perhaps it is empty, perhaps it is filled with stars, perhaps it evolved differently. Perhaps intelligence there wonders whether something lies beyond their reality too. We are not alone in asking the question. We are alone in our inability to reach the answer. We end this chapter with a thought that will guide the final one. If the fifth dimension exists, then our senses show us only a small slice of reality. What we call the universe may not be everything. It may be only the visible face of a deeper structure. The final chapter brings the idea full circle. When people search for truth, they rarely expect the truth to reveal emptiness. For most of human history, we believe that what we see is all that exists. The earth was the center. The stars were lights pinned on a ceiling. Beyond that ceiling was nothing. We lived in a small universe with small questions. Then the telescope shattered that illusion. We saw worlds beyond worlds. The solar system became a small neighborhood. The galaxy became a single city in an endless cosmic continent. Every time we discovered more, our importance shrank, but our awe grew. Yet the most radical shift was still waiting. We learned that matter is mostly empty space. Atoms are tiny nuclei surrounded by a cloud of probability. The solid world is not solid. Then physics stripped away even the nucleus, revealing quarks and fields, and suddenly the universe was not built from things, but from excitations. Then we learned that space is not a stage. It is an actor. Gravity is not a force. It is the geometry of space-time. Einstein replaced gravity with curvature. A mass bends space. Space tells matter how to move. Reality became a conversation between mass and geometry. But even that revelation was small compared to what came next. Kaluza proposed a fifth dimension. Klein realized it could be curled too small to see. String theory demanded not 5 dimensions, but 10 or 11. Brane theory transformed the entire universe into a four-dimensional membrane, floating in a higher dimensional ocean. Gravity became weak, not because it is gentle, but because it leaks. Dark matter stopped being an exotic particle and became possibly a shadow of matter in another dimension. The Big Bang stopped being the beginning and became possibly the collision of brains. Every chapter of discovery revealed not emptiness, but depth. The universe is not a stage where physics happens. The universe is architecture, a structure, a blueprint woven from geometry and vibration. We live inside a design so vast that even our best equations touch only a fraction of it. We have spent centuries drawing maps of the visible. Only now do we realize the visible might not even be the main feature. Our sensors measure light, our instruments measure particles, but we are blind to everything that does not live on our brain. We treat the universe as if it is everything because we evolved within it. A fish cannot imagine air. A person born underground cannot imagine stars. Our senses were sculpted by survival, not truth. We see only 3 spatial dimensions because our biology requires only 3. Evolution needed movement across land and depth perception, not access to higher dimensional space. The 5th dimension offers no survival advantage. Thus, we do not perceive it, but nature does not care what we perceive. Scientists measure gravity with obsessive precision. They observe that it is weaker than the electromagnetic force by a factor beyond comprehension. A magnet the size of your hand lifts a paperclip against the pull of an entire planet. This inconsistency should not exist in a universe with only 3 spatial dimensions. It only makes sense if gravity has more space to spread into. Gravity may be the only force that refuses confinement, the only force that touches all dimensions. If that is true, then gravity becomes our messenger. It carries information from the dimensions we cannot touch. Every time a star orbits, it interacts with the bulk. Every time a galaxy rotates, it traces the geometry of something beyond us. Dark matter halos might not be halos of matter. They might be dimples in the brain created by gravity leaking toward mass on another brain. The missing 95% of the universe might not be missing at all. It might simply be misplaced. We search for dark matter as if it hides within our world. But what if we are the ones who are hidden? What if our universe is a shadow? In the brane collision theory, our universe was born when 2 brains touched. That collision released enough energy to ignite space-time, to form the first atoms, to set the expansion of the cosmos into motion. The Big Bang was not an explosion. It was a transfer, a handoff between dimensions. If that theory is true, then creation did not happen once. It happens repeatedly, as brains drift and collide over unimaginable spans of higher dimensional time. The universe might not be a singular event. It might be a cycle, a rhythm, a heartbeat. Every collision leaves a universe behind. Every separation stretches that universe into expansion. Every approach sets the stage for another collision. Reality becomes a vast breathing structure, inhaling and exhaling existence. In this view, the universe is not a miracle. It is inevitable, and we are simply inside one breath. These ideas do not weaken science. They strengthen it. A theory that explains more than its predecessors is a better theory. A theory that makes predictions that can be tested is an honest theory. Extra dimensions predict missing energy signatures in particle colliders. They predict heavier Kaluza-Klein particles. They predict specific patterns in the cosmic microwave background. They predict miniature black holes at energies just beyond our current technology. The most radical ideas in physics are also the most vulnerable. They must face the universe. The universe does not care what we believe. It will answer only when we are capable of listening. This is where the story leads. Our universe is not a box with walls. It is a surface with depth beneath it. We live inside a dimensional ecology. Gravity drifts, matter hides, dimensions curl. The universe is not a sphere, it is a membrane. The membrane is not the whole. It floats in something deeper. We are not central. We are not alone. We are not complete. And that realization should not make us feel small. It should make us feel awake. Look at your hands. Every atom in them once existed in a universe that did not yet exist. Your body is made from the ashes of stars formed after a collision of brains. The iron in your blood was forged in the heart of a star that lived billions of years before Earth existed. Your atoms carry memory older than the universe you inhabit. When you look at the night sky, you are not looking out. You are looking across. The stars do not mark the edge of reality. They mark the edge of what we can perceive. Imagine lifting that sheet of paper again. Instead of drawing a dot, imagine being the dot. Imagine discovering that the sheet is not flat. It bends, it flexes, it ripples. Imagine discovering that above and below, there are directions you can never travel, but that still exist. Now imagine learning that somewhere on the sheet next to you, there are other dots, other worlds, other realities, separated not by distance, but by dimensional confinement. That is the hidden universe. We may not be at the center of the universe. We may not even be in the center of dimensions. The universe does not hide its truth out of cruelty. It hides its truth because we have not yet built the tools or the minds to reveal it. For now, we observe shadows. We measure leaks. We infer the existence of something deeper from the distortions it creates. One day, a detector will see missing energy with perfect clarity. One day, a Kaluza-Klein particle will emerge from collision. One day, a gravitational signature in the cosmic background will match the pattern of a Brane collision. On that day, humanity will understand that reality did not become stranger. Reality was always this strange. We simply became able to see it.